you're taking a region and rotating it around an axis. Here you're creating a volume by starting with some kind of function and creating shapes on that function. This shape right here, as exciting as it looks, it is a circular base, and then all the way throughout the thing is the cross section is a square, even though it doesn't look like that, right? If you sliced it the way those cardboard pieces are. There's a few things online here that are going to help you visualize this a little better. So before we start calculating anything, it's important to understand how we're creating these shapes. Hopefully some of these sites are going to work here. This is just something online here, and obviously the way YouTube works, this is the most related video to this one. It's an ad. It's a feature video, yes, because when you look for finding volume by cross sections, you obviously want to look at Canada's career expert. I'm not sure whether there's any sound, but the sound is off, and it doesn't really matter, right? But if you have some kind of a region that's defined by a function somehow, you can create a solid by saying the cross section kind of rising out of the page is a certain shape. That is supposed to be, I guess, semicircles. They're not quite semicircles, but so you create some solid that comes from that, and then you have all kinds of other things there. Here's another one where the same region, but now the cross sections are going to be something else. Okay, rectangles. So you create a solid where the cross sections, right? If you slice it anywhere, the slices you get are rectangles. And okay, eventually then the base looks the same as the other thing that we just looked at, but the shape, it's got those those edges on it. So this is called volumes, where you have volumes of a known cross section. Okay, where you have a cross section that you're following. This was going incredibly slow before, so we can try looking at it. Here's two functions where there's an intersection. So there's a region. So if you're looking straight down on the graph, you have this region here. But then it's saying, rising out of the page is the cross sections are squares, right? So let's try doing this. If I slide this thing, I was hoping that the thing would move. No, my internet's going very slowly right now, but anywhere you go with this, it's not going to change very quickly. Anywhere you go from one end to the other there, okay, the square is getting smaller as you go from one end to the other, okay? The cross section is always a square, though, no matter where you go. Okay, so if you know these functions, you can use them to come up with the dimensions of the square. Remember that the volume is just the integral of the cross-sectional area, right? If you integrate the cross-sectional area, you get the volume, right? Because basically what you're doing is you're summing up all these little, they're not discs here, they're flat square-shaped things, rectangular prisms. And then if you take the limit of the sum of all those flat pieces, you get the solid, right? So if we do this, okay, the thing's going to eventually look like that, right? Something like that. Okay, but you're going to approximate it with rectangles. So you're writing you're doing exactly what you did last time. It's just that the area is not pi r squared, right? Or pi big R squared minus pi little r squared. It's just, for this it's almost easier sometimes. You don't have pi involved. You just have the area of a square. The difference between those two functions, right? X squared, sorry, not that one. 8 minus x squared minus x squared, right? That's the difference in height. 8 minus x squared minus x squared. And then that whole thing squared. That gives you the area of the square. If you integrate that from that point to that point on this axis here, you get the volume, okay? So this one doesn't show it as well, but you can calculate the volume just by, again, whatever your two functions are. Look at the difference, if there's a difference, or if it's just one function. But the key is coming up with the expression for the cross-sectional area, like you would have before. Okay. So the first thing here is coming up with the volume of a shape that looks like this. As far as a real life thing that looks like that, the best I can do for you is if you're driving around, sometimes you see at the side of the street, like it must be like the sewer or something needs vent pipes, and there's pipes sticking out of the ground that are black or brown or whatever, then they have a yellow cap on the top. The yellow cap is shaped like this usually, sometimes. I have no idea why it's shaped like that, but it is. I'm sure not to do with because you can figure it out using calculus, but remember that the volume formula, if you want the volume of something, it's just integral from whatever boundaries you're using of whatever the cross-sectional area is. Right? This is just cross-sectional area. So before that was pi r squared, or pi big R squared minus little r squared, right? Before, when we were doing volumes of rotation or revolution, that was something to do with pi. Here it's going to be sometimes easier, right? Because it's a square or whatever, right? This is just the cross-sectional area, right? An expression for that. You can write some kind of expression for the cross-sectional area, and then you integrate it the other direction, right? So if you're on this thing here, whatever that cross-sectional area of the square is, and then integrate it perpendicular to that, you get the volume, right? Because the area is two-dimensional, and then when you integrate it in the third dimension here, you get something, the result is three-dimensional. Okay, so the first thing you can generate by doing this, again, the hard thing, the reason people find this hard is because it's hard to visualize. It's hard to draw the three-dimensional thing on two-dimensional paper. But if you can visualize it in your head, it's not all that hard, right? Now, the other possible problem we run into is we're not necessarily as familiar as we should be with circles and things like that, because you learned them a little bit in grade 11, but they took what you used to do a lot of in grade 12 was taken out a couple of years ago. But hopefully, nonetheless, you can still figure out what the equation of a circle is here, except for my circle's not really a circle there. It's kind of an ellipse, and it's not even in the right center, is it? So if I fix this up here a little bit, well, on my screen it looks like a circle, but on yours I don't know. We'll see. Does that sort of look like a circle? Let's pretend it's a circle. Might be an ellipse, but let's pretend it's a circle. When the equation looks like that, what's the radius of the circle? Radius is 3. So this is 3, this is 3, negative 3 there. If you wanted it to be centered somewhere else, you would replace x with like x minus 1 or something like that, or y with y plus 2. That would shift it somewhere else. We don't have that involved here. So what it's saying here is the base of this shape is a circle. So this is this shape right here. The base of this thing is a circle, and every cross section is a square. It's probably hard to tell in your photocopy what that looks like, but I have an actual model of it here that some former students made. You can look at after. So perpendicular to the x-axis, right? So there's the x-axis perpendicular. So it's again hard to draw, but rising out of the page here is these rectangles. I won't even try and bother drawing it there. What I'm going to do is say, perpendicular to the paper, coming out of the paper is this thing where it's a square, right? That's really weird how that works. Let's try again. That's sort of like a square, isn't it? What you have to do, though, is say, what are the dimensions of that square? If this is so I'm going to put this here, and that's meant to represent that, right? But the square is tipped up vertically coming out of the page. What are the dimensions of that square? This height here is y, right? So then this thing must be how much? 2y, right? So you got 2y. And then if it's a square, this has to be 2y. So then the area is, what's the area? 4y squared, right? Or in other words, if the area is 4y squared, but we're going to be integrating it dx here, so we need it to be in terms of x. So we need to substitute something in there for what y is, right? We need to take this and rearrange it for y, or actually y squared, because you can sub in if you're clever here, you can realize that you're subbing something in for y squared. So if you want to, you could say y squared is 9 minus x squared. Y is square root of 9 minus x squared. If you want, you can put in square root of 9 minus x squared, but then realize that you're squaring it. What do you get? 4 9 minus x, right? Or if you want to multiply it out, if you don't want the brackets, what is it going to be? 36 minus 4x. That's an expression for the cross-sectional area in terms of x, right? 36 minus 4x. Not really, because I forgot a squared there, sorry. How about that? Let's make sure we get the squared in there. I missed it. That's the cross-sectional area. If you have the cross-sectional area, then the volume is going to be if you integrate it perpendicular to that, right? So if the slices are vertically coming out of the page and you integrate it in that x direction, you get the volume, right? Because this is already going to be square centimeters or square meters or square kilometers or whatever. Integrate it the other way, you get cubic units. So we need to go integral from something to something. What are those two somethings? Negative 3 and 3, because we got to go from here all the way up to here, right? Where it starts and ends. So where it starts and ends of the area, right? Negative 3 to 3 of the area. Now I could actually put in what the area is, because I'm pretty sure we know that, right? The area is, what did we say it was? 36 minus 4 x squared. That thing is the cross-sectional area, right? Cross-sectional area, right? If you integrate the area dx, you get this. I guess if you wanted to be clever and just different, instead of going from negative 3 to 3, what could you do? You could go 0 to 3 and then times it by 2 if you wanted to. So there's no one exact way to do this, but we can stick to this for now. I don't care if you do this again with the calculator or algebraically. If you were doing it algebraically, you'd have to find an antiderivative of this 36x minus 4/3 x cubed, right? I think. Is that correct? I'm pretty sure. And we have from negative 3 to 3. If you didn't want to do all that calculating, you could, again, times it by 2 and start at 0 instead. It's fine to just put the answer if you want. What is the answer to this? Should we go to the calculator? What if we break out the T84 silver edition just for fun? That'd be worth it? Not really, but it's the same machine. If you're trying to work that out as, why don't we say 36 times 3 minus, if you want to be fancy, you can use the fraction thing here, 4/3. And we've got times 3 power of 3. Is that right? Is that right? When you put a negative 3 in there, when you put negative 3 in there, both of these are going to be negative. So when you subtract a negative, it's going to be adding. So it is just going to be double that, right? I'm not going to spend my time typing that in again. Right? It's going to be 144. As far as I'm concerned here, is that right? And it's, cubic units. I don't know what you want to put here. Units cubed, whatever they are. If you don't know what the units are, you can just say that. Let's think carefully about these other questions here, because again, it doesn't, just because it's suddenly now a triangle or something, the shape would look totally different. But using this approach, like, it'd be pretty hard if you had the two shapes sitting side by side. Unfortunately, I don't have a picture or an actual model of what this would look like if it was triangles all the way through, but basically what it would be is you'd have, this would be a big sliced kind of that way. all the way through, every single one of them be a triangle. But if you know that every single one of them is a triangle, how's the volume going to compare? It's going to be half as much, right? If every single one of them was a isosceles triangle with one leg in the plane of the base, what that means is one leg in the plane of the base means one leg's there. Isosceles right triangle means the other leg's there like this. Okay, so it's going to be half as much, right? If you want to draw some kind of a triangle there, right? That's what it's going to look like. It's going to be exactly the same, right? 2y, 2y. So the area is going to be 4y squared divided by 2, right? 2y squared. You have 4y squared here, it's just going to be half as much. You can go through and do it if you want. I mean, the expression, maybe we could write the expression here, negative 3 to 3 of, it's going to be half that much though, right? It's going to be 18 minus 2x squared dx dot 72. What about if the cross sections were equilateral triangles with one side in the plane of the base? So now you're saying, if it was equilateral triangles, this distance, that distance, that distance, it's not going to be quite as high as the square. Right? If it's an equilateral triangle, the height's not the same as the width. So you need to do a bit of thinking here first for equilateral triangle. The hard part is coming up with the area expression, right? If this is your equilateral triangle, sort of, pretend that's an equilateral triangle. What do we have here? What's our, the base of the thing is still 2y, right? Base of the thing's 2y, but what's the height of the thing? What's this height? How do you find the height? If the base is 2y, one of them is y, right? Yeah, you can either use those exact values, root 3y, or you could use trigonometry if you want. That's 60 degrees. If you really wanted to and you say, I don't know that, if you don't know that 1, 2, root 3 business, you could use trig, right? You could just quickly write something with trig. You could say, if this is h, you could say tan of 60 equals h over y. So y is h over tan 60 if you really want to. Except I wanted it the other way around, didn't I? That was dumb. I want the y by itself. Y times tan 60. Right? Move this thing over here. Y tan 60. You could put that in there. Work out what tangent of 60 is if you don't happen to know it. And work it out. Put that in there, right? Tan 60 is root 3, right? Or 1.73, whatever. You can, if you want, put 1.73, whatever it is, times y. However you work that out, right? As long as you can get the area. Okay, we don't want to go back to all the geometry, grade 10 and 11 or whatever, but if you're working this out that it's 2y times root 3y divided by 2, right? Or in other words, if you simplify that, root 3y squared and no divided by 2. However you get the area, the volume is easy, right? Negative 3 to 3 of, well, it's going to be root 3 9 minus x squared squared. Well, just that then, right? Yeah. Dot, dot, dot. Anyways, the hard part is doing this, thinking through what the area of the cross-section is. Finding the area, that's the key, right? So there's lots of problems to do in here. I think you're going to find that, I'll go back to that in a sec if you want to copy that down, but there's not tons of problems in here. There's some, and they're just, here's a curve, or here's a shape, right? You got to find, it says the base of the region bounded by, sine x, and the x-axis between 0 and pi, so it's this area in here. The shapes rising out of there are squares, right? So cross sections coming out of there are squares, or they're semicircles. You got to think about the area of a semicircle. I'm pretty sure you can do this, right? And there's another one there with weird curves intersecting, this one and this one, and that other line. But same thing, right? There's a few extra questions. You don't need to do those if you feel like you get the concept by that time. And then I think we should be good. I think you have enough time here to at least get these problems done and then work on some of your assignments, all right?